Well, we're going to spend a little time talking about graphing now, and graphing is a really easy and powerful method to visualize the relationship between position and velocity and acceleration. Let's say we have this particle that is traveling along this straight line at a constant speed. If it's a constant speed, that means that if I look at a velocity versus time graph, we can see that velocity is going to be a constant positive number. If velocity is constant, that means the speed is not changing, which means that acceleration is going to be equal to 0 versus time. If the speed is not changing, but it is moving, obviously it is moving, that means its position, the distance away from the origin, is increasing at a positive constant rate. So, and it increases linearly with respect to time. So it's pretty easy to see something easy like that. The concept gets very powerful when we have erratic motion. And erratic motion is defined as when a single equation does not appropriately define the motion over the time frame that we're considering. So if there's not one equation that defines the motion, then that means we have to break it up into pieces, and a graph is an easy way of doing that. For example, now let's say that this particle is going along in a straight line, then it stops, and then it goes back at the same speed, and then it stops again. So we can see that the velocity is going to be a positive number for a little bit, and then it's going to be a negative number for a little bit, and then it's going to go to 0. If we look at the position is really easy to see. It's going in this way for a little while, which means it's increasing, and then it comes back on itself, which means it's decreasing, and then it stops, and that means position versus time becomes a straight line. If it's constant speed, obviously acceleration is going to be 0. There may be a little blip while it changes direction, and then it's going to be 0 because it's going to be constant speed going back. So acceleration pretty much is 0 the whole time, except for this little small discontinuity in the acceleration here for changing direction. Okay, so a couple things about graphing which may be obvious, but let's just mention it. Let's say that, or let's recognize that time marches on. So if you had a position versus time graph, you'd never see it coming back on each other because time can never go backwards. The same with velocity, can never go backwards on itself. The other thing is that there cannot be discontinuities in position or velocity. In other words, you can never have an instantaneous change in position. If time hasn't changed, you can't see an instantaneous change in position like that. That doesn't exist in real life. Same thing with velocity. You'll never see an instantaneous change in velocity versus time in real life. However, you can instantly change acceleration. It's pretty easy to have a positive acceleration and then instantly have a different acceleration on a versus t graph. Okay, how about some relationships between s and velocity and acceleration? So if you have a curve, position versus time, and we know from calculus that the slope of the position is the first derivative. If you have an equation that defines this line, then the first derivative is called the slope. And so the first derivative would be ds dt. That would be the slope, would be ds dt. We recognize ds dt as velocity. Therefore, the slope of the st graph is going to be the instantaneous velocity. Same with, or similarly with velocity. If you have a velocity versus time graph, we know that the slope at any position evaluated anywhere is going to be dv dt. We recognize dv dt as acceleration, so therefore the slope of the vt graph is the instantaneous acceleration. Now, what about the area under the curve? If we integrate a vt graph, we integrate it from here to here, we would get the area under the curve. Well, if we look at v is equal to ds dt and manipulate it into ds equals v dt, the area under the curve is the integral of v dt. So if I integrate the integral of v dt, I get the integral of ds, which means that is the change in displacement. So the takeaway here is that the integral of VT, or the area under the curve of a VT graph, is going to be the change in position, or the change in displacement. And similarly then with an AT graph, the area under the curve here, A equals dv dt, dv is equal to A dt, and so if I integrate both sides there, I can see that the area under an AT graph is the change in velocity. Okay. How about this guy? This is the way some of you drive, I know, but let's say that you're driving in your car and you're accelerating at a rate of speed, and instantly you touch your brakes and all of a sudden your acceleration goes from positive to negative, and then you let off the brakes and now you're going to coast for a little while and now you have zero acceleration. It's pretty easy then to see with our previous understandings, if I have a positive constant acceleration, velocity is increasing linearly. If the acceleration now becomes negative but it's still positive, but if it's constant, then I have it decreasing velocity, and as soon as acceleration becomes zero, then I have a constant velocity. All right, and what I'm going to say here is that the slope here is equal to the value of acceleration. So if I have a positive acceleration, I have a positive slope. If I have a negative acceleration, I have a negative slope, meaning it's going downhill. Okay. And then the position versus time graph is it comes from the velocity graph. So if we know that if this is increasing linearly, this is going to be a quadratic of some sort, and if it decreases linearly, this is going to be a quadratic, and then when it becomes constant velocity, then position increases linearly with time. Now, the blending here is called parabolic blending, and what we'll find out is the transition between points on a position graph are always going to have the same slope. So when we see these things evaluated there, the slope at the end of this curve is going to be the same as the slope of that beginning of that curve. Same thing here. The ending of this slope is going to be the same as the beginning of that slope. So parabolic blending generally occurs when we do ST graphs. Okay, let's talk about a little problem then. Let's use the area under the curve technique to solve a little bit here. So here we have a car that's got some acceleration, and we're going to say he starts at zero acceleration at time is equal to zero, but his acceleration increases it doesn't increase linearly, it increases with this curve right here. And then after a certain number of time, looks like 6 seconds, then he has constant acceleration. Let's use the area under the curve technique to figure out what his final speed is. And we know that the area under the AT graph is going to be the change in speed. All right, so from here, and we can see that this is erratic motion because there's not one equation that fully describes the motion between 0 and 10 seconds. We have something that describes it between 0 and 6, and then something else that describes it between 6 and 10. So we'll have to break this up into two pieces, and let's say from time is equal to between 0 and 6, we're going to find out what the area under that curve is, and that'll be the change in velocity for that. So we say the area is going to be the integral of 1/6 t squared dt, and that's going to be equal to 1/6 t cubed over 3, evaluated from 0 to 6, and I can say that that is equal to 12. So that is going to be in meters per second, so the change is going to be the change in velocity is going to be 12 meters per second between 0 and 6. All right, what would be the change in velocity between here and between 6 and 10? Well, it would be this area. So I got two areas under the curve that I'm going to evaluate, and then between 6 time between 10 and there. So we're going to say that the area is going to be equal to, looks like I got 4 times 6, so 4 times 6 is going to be equal to 24 meters per second. So that's going to be the change, come on now, pencil, the change in velocity from there to there. So the final speed is going to be equal to this 12 plus 24, so that's going to be equal to 36 meters per second. Sorry about that, I'm breaking my pencil. So the final speed is going to be equal to 36 meters per second. So that's quite easy to do that, and we'll use more examples as we go forward.